Okay, let's dive right in. Announcements are the same as yesterday. Well, I guess not exactly the same. No homework due tonight, but homework due next week. Make sure you get started on it. It's over mostly partial fractions. There are a few trig substitution problems on there as well. So make sure you get to work on those. And if you have any questions, let me know. All right. So let's dive into this partial fraction decomposition. This is where we left off last class. We broke down this function, 3x squared minus 3x minus 2, into its partial fraction decomposition, where we still need to find a, b, c, and d. But we know this is the right guess to make. Why do we know that? Because I told you. Okay? So, but also it's what makes sense with how we add fractions, right? So let's start solving for a, b, c, and d. Just like last time, and just like every time you do any of these problems, you write down the partial fraction decomposition, and then you add it right back up. You pretend you don't know where this came from, and you try and simplify it as far as possible by getting a common denominator and adding everything up. So the common denominator, by design, is just going to be this x plus 1 times x minus 3 cubed, right? That's exactly what we want the common denominator to be. So this is going to be, well, I'll multiply that first term, top and bottom, by x minus 1 cubed. And that'll give me a times x minus 1 cubed for my first term over x plus 1 times x minus 1 cubed. Then plus the second term, I'm going to multiply top and bottom by x plus 1 times x minus 1 squared. Okay, and I'll end up with b times x plus 1, x minus 1 squared. Next term, I'll get plus c times that one. I'm going to multiply top and bottom by, well, again, in the bottom, I want x minus 1 cubed times x plus 1. So I need to multiply by 1, x minus 1, and 1, x plus 1. Okay, and so when I do that, I'm going to get x plus 1 times x minus 1. And then the bottom, again, is going to be that same common denominator. And then lastly, plus d times, the only thing missing from this last term is the x plus 1 in the denominator. So I'll multiply top and bottom by x plus 1. Okay. And then now all of those have the same common denominator. So x plus 1, x minus 1 cubed. And really, the denominator is, it's nice to check and make sure that we got the right common denominator. But now we're going to essentially forget about it, because this is supposed to be equal to this thing, and their denominators are the same. So that means their numerators have to be the same, right? So I get,
that's equal, sorry,
no, go for it.
That's equal the a where we did all its common denominators.
Yes,
To the 3x.
exactly right.
Not the a. Well, yes, the ABC, but
It's also equal, exactly,
we're
yeah.
set it equal to 3x squared.
Exactly, exactly. All these things I have written are equal to each other, but the two important ones to set equal to each other are the two I have circled. So the numerators are going to have to be equal. So 3x squared minus 3x minus 2. This is equal to a times x minus 1 cubed plus b times x plus 1 times x minus 1 squared plus c times x plus 1, x minus 1, plus d times x plus 1. Okay. Questions so far? All right, how do we want to tackle this problem, solving this equation here for a, b, c, and d? Because again, it has to be equal for every x. we have two methods we could try. We could try equating coefficients, and we could try strategic substitution. I'm going to tell you, so that nobody gives me the answer I don't want to do, I'm going to do strategic substitution on this one, because there's one hiccup with strategic substitution, but it's still a little easier than equating coefficients for this problem. Okay, so let's do strategic substitution. Strategic, I'll just write strat sub. Okay, strategic substitution. There's two numbers right off the bat that should be pretty obvious that I want to plug in. What are those two numbers? 1 and -1, right? The zeros of the denominator. And it's actually, if anyone wants to see the proof of why I'm allowed to plug in 1 and -1 into the numerator, because really we shouldn't. But it's actually a very happy coincidence that we're able to. Not a happy coincidence. I mean, mathematically, you can prove it rigorously. But you're actually allowed to plug in any x into this equation here. So I'm going to plug in x equals 1. And when I do that, I get x equals 1. Well, on the left, what am I going to get? I'm going to get 3 minus 3 minus 2. So that's going to give me just minus 2. So on the left, I get minus 2 when I plug in x equals minus 1. Or sorry, when I plug in x equals plus 1. And on the right, well, when I plug in x equals 1, this is going to be 0, this is going to be 0, this is going to be 0. I'm only going to be left with the d part. Okay, so when I plug in 1 into that last term, I'm going to get 2 times d. So I get -2 equals 2 times d. And that tells me what? D is equal to
-1.
-1, exactly. Divide both sides by 2. So we've got one coefficient right off the bat, like that. Easy squeezy. The other number that makes the most sense to plug in, as Mark said, is -1. So when I plug in -1 into the left-hand side, well, I'm going to get 3, now plus 3, and minus 2. So 3 plus 3 is 6, minus 2 is 4, is equal to. Now on the right-hand side, let me erase these underlines. On the right-hand side, when I plug in -1, notice that this term and this term and this term are all going to be 0, right? That's the whole point of strategic substitution, is I pick the numbers that are going to make the most things 0. Okay? And so when I do that, I will only be left with this term. So -1 cubed is -2 cubed, because -1 minus 1. So -2 cubed is -8. So I'm going to get 4 equals -8 times a. And that tells me that a is equal to -1/2. Okay, so now those are the only two numbers in strategic substitution that it makes a lot of sense to plug in to make everything as 0 as possible, right? What should I do next? What do you think? Remember, this is supposed to be an equation that is true for every x. So what would you like to do? Other than have me tell you the answer. Five, 4, 3, 2, 1. Here we go. So it's not obvious until I tell you, and then you're gonna be like, oh yeah, it's like the twist at the end of that show. Okay, so if you plug in just any other number, you'll get another equation that has only A's and really no A's and D's, because we solved for A and D. But it'll only have B's and C's and numbers, right? So when I plug in x equals 0, well, and why did I pick 0? Well, 0 is a great number. 0 also will leave me with something nice over here. And when I plug in 0 here, I'll get -1. When I plug in 0 here and here, I'll get 1 times -1. 0 is not the most convenient, but it's probably the next most convenient after 1 and -1. So strategic substitution, we're still picking numbers that, yeah, maybe they're not making everything as zero as possible, but they're making everything as nice as possible. Okay, so that's why I picked 0. Sometimes it might make more sense to plug in 2 or something. Okay, so if I plug in 0 here on the left, I get -2. On the right, I'm going to get, well, when I plug in 0, I'm going to get -1 cubed is -1, so I'm going to get negative a, which we know is 1/2. So I'm going to substitute that right away. So negative a is negative 1/2, so that's positive 1/2. Okay. So there's the first part when I plug in 0. When I plug in 0 into this next term, well, when I plug in 0 here, I'm going to get 1. Here, I'm going to get -1. So I'm going to get it squared. So the next term is just plus b. Okay? Plus b. Next term, when I plug in 0 here, this is going to be a positive 1. This is going to be a -1. So the next term is just minus c. Why did we leave the, well, if I had an a, we know what a is, so this is going to give us an equation that only has b's and c's. Yeah, good question. Good question. So then minus c, and then the last part, when I plug in 0 into this last term, I'm just going to get 1 times d. But again, we know what d is already, so let's plug in what d is. So 1 times d, that's going to give me -1, because d is -1. Okay. So getting everything on one side that's not a b or c, I'm going to get b minus c equals -2 plus 1 is -1, and then -1/2. So that's -3/2. Questions on where this equation came from? All right, and then we need one more. We have 2 unknowns now, right? B and C, but I only have 1 equation. So I need 1 more equation, right? Where is that equation going to come from?
Plug x equals 2.
Yeah, exactly. I can plug in x equals 2. X equals 2 is going to make all the x minus 1s. It's going to make all of those +1, which is very easy to work with. So x equals 2 is another pretty convenient choice. Not the most, but in this case, we've already dealt with the most convenient. We have to deal with something that's only pretty convenient. Okay. So when I plug in x equals 2, well, on the left, I'm going to get 3 times -2 squared. So 3 times 4 is 12. I'll actually write this one out so I don't screw it up. Minus, bless you, -3 times 2, bless you, so -6, and then -2, which is 6 minus 2 is 4, right? So we get 4 on the left. On the right, when I plug in x equals 2, well, again, 2 is a pretty convenient number because that's going to make this first term, the x minus 1, all the x minus 1s, it's just going to make those 1s, which are pretty nice. So I'm just going to be left with a, which is, again, -1/2, plus b times, when I plug in 2 now, I'm going to be left with a 1 here and a 3 here, right? So when my next term is plus 3b, when I plug in 2 into this term, I'm going to be left with, again, a 3 and a 1. So plus 3c. And then the last term, plug in 2, I'm going to get plus 3d. But d is -1, so -3. So getting my b's and c's, again, on one side by themselves, I have 3b plus 3c. This is equal to 4 plus 3 is 7 plus 1/2. So that's what, 15 over 2? Questions so far? Okay. And then from here, we have two equations, two unknowns that we need to solve. And to do that, you can do this using any method. This is something that you should have been able to do before coming to this class. But I understand also getting in calculus mode and forgetting how to do certain problems. So let's look at this. We have b minus c. B minus c is equal to, was it 3/2 or minus 3/2? Minus 3/2, thank you. Minus 3/2. And then 3b plus 3c is equal to 15 over 2. The first thing I would do is the 1/2s are annoying, so I would multiply both of these equations, both sides, by 2. Okay, and when I do that, on the left, I'm going to get 2b minus 2c is equal to minus 3 for the first equation, because again, the 1/2 is super annoying. And then on the second equation, I'm going to get 6b plus 6c is equal to 15. So that was multiply both equations by 2. And then from there, I would, again, you can solve for one variable and plug it in to the other equation. I'm going to multiply the top equation by 3. Top times 3. And when you do that, you get 6 times b minus 6 times c equals minus 9. And why did I do that? Well, because the bottom equation also has 6b and 6c. And so now I can solve for b by adding both equations to each other, right? When I add these up, I get 6b plus 6b is 12b. 6c minus 6c plus 6c is 0. And then minus 9 plus 15 is what, 6? And that tells me b has to be 12. Or sorry, 6 over 12. That would be some new math. Okay. Or in other words, b is 1/2. I could have also, questions? I could have also subtracted these. You could plug b equals 1/2 back in to these equations, or you could also subtract these two equations. If I were to subtract these two equations, I'll get 6b minus 6b gives me 0. Minus 6c minus 6c is minus 12c. And minus 9 minus 15, that's minus 24. So that tells me c is equal to minus 24 divided by minus 12 is 2. Okay. So we have our partial fraction decomposition. Okay. So we have a and d. So we can actually rewrite. I'm going to rewrite just right here. So a was the thing over our first term. So that's minus 1/2. So let me move this out a little bit. This is equal to. I like to write my constants out in front like this. So minus 1/2 times 1 over x plus 1 plus b over my next guy. So b was plus 1/2. Okay, so plus 1/2 times 1 over x minus 1. C was 2. So I'll write plus, I'll just write 2 on top. When they're fractions, I like to write them out in front. When they're integers, I like to write them on top like that. Doesn't matter. And lastly, d, well, d was minus 1. minus 1. Okay? And that's the partial fraction decomposition of this rational function. Do we have questions on that? I'm going to copy and paste that. Not copy and paste, but copy it. Because it's going to be important here in a second. Yeah.
So, correct me if I'm wrong, is the difference between non-repeating unit factors and repeating? Are we taking the integral of the non-repeating ones?
We're taking integrals of all of these.
You haven't just done that?
We just haven't done it yet.
Okay.
Yeah.
And
That's the motivation is if you want to integrate that thing up top, well, that sucks. I don't want to do that. But this sum, that's not that bad, right? That's the whole motivation.
And then I have one more question.
Yeah.
When we're deciding that we get to, when we're doing a times x minus 1 plus b, that whole new,
Mm-hmm.
how do you choose which ones you want to multiply by each letter?
You're trying to get this common denominator. Oops. You're trying to get the common denominator of x plus 1 times x minus 1 cubed. And so when this was just a over x plus 1, well, I want a over x plus 1 to have the denominator of x plus 1 times x minus 1 cubed. So I just multiply top and bottom by that. That's how I do that. And the same with b and c and d. All right, so let's look at how this is actually used. We actually use this to integrate stuff. So this integral is, I want to come back to this, but the integral is going to be, when I write this out in terms of the partial fraction decomposition, well, hopefully you all copied that partial fraction decomposition as well. This rational function is exactly the one that we just found the partial fraction decomposition, which was this thing, right? This integral is equal to this integral because we broke it down. We broke down the thing inside the integral into this partial fraction decomposition. Okay. So let's take 1 minute. Everybody take 1 minute and figure out what this integral needs to be. Go. All right, I don't expect anyone to be done. I want to get through some other stuff. So someone tell me, how did you handle this integral and this integral when you broke this apart? Yeah, that's the natural log of these guys, right? The natural log of x plus 1, and we see this by a u substitution. U is x plus 1, and really all of these you're going to need I call it a baby u substitution, right? U is x plus 1 in the first one, and for the other three, u is x minus 1. So on these first two, I'm going to get minus 1/2 times the natural log of x plus 1 in absolute value, and then plus 1/2 times the natural log of the absolute value of x minus 1. Again, beta u substitution. This one, and I gave it away, use the u substitution, and when you go through and you make that u substitution, this will end up looking like 2u to the minus 2, right? Where u is x minus 1. But that's just the power rule, right? For that, to integrate that, you add 1 to the exponent, divide by the new exponent, and so you'll just get minus 2 u to the minus 1, which would, in this case, just be minus 2 over x minus 1. This one, again, people hear me at home? Yeah, okay. So the last integral, again, and this, you'll get the exact same thing. This is minus 1, so minus u to the minus 3. Power rule, switch back, and when you do that, you end up with this. So this is the real power of partial fraction decomposition. Every time you break down one of these rational functions, I know it seems like a lot of work, but we're sort of front loading the work to make the integrand look like something that's easier to integrate, right? We do all the hard work in breaking that down so that the integration, which is usually the very hard work, then becomes, I won't say easy, but easier. Okay? All right. So that was linear factors and repeated linear factors. We looked at really both of those in this example. Sometimes when we're factoring q, we'll end up with something that looks like this, maybe 2x plus 3 times x squared plus 4. And we work with real numbers. You can't break down x plus 4 anymore, right? If you try to find a 0 of x squared plus 4, well, you would do x squared plus 4 equals 0. So x squared equals minus 4. No such real number does that, right? If you're a math major, later, and you all have probably heard it on imaginary numbers, but we work with real numbers in class. Okay? So sometimes it's going to be unavoidable that q will have quadratic factors as well. Okay? It's not a repeated linear factor. It's a totally new case. We need to be able to handle this case in addition to the two cases. Okay. So, fortunately, not much changes. There's a small change that we need to do when we're writing down our partial fraction decomposition, but it's going to look very simple. Okay, so for this specific example, no matter what p is, I'm going to break down if q, the bottom, is 2x plus 3 times x squared plus 4. Then the partial fraction decomposition becomes, well, for this factor, we've dealt with that, right? That's a non-repeating linear factor. We just get this a1, or a over 2x plus 3. Then for the quadratic factor, that one we need to handle a little different. This one could look like, it could just be some constant. We could go through and work out all the numbers, and it could be the case that it's just 1 over x squared plus 4. But there could also be something times x in the numerator for this second part of partial fraction. Okay? So when we have quadratic factors, that's what we need to do. We need to add this sort of linear term in the numerator. But that's the only thing that changes. From there, what do we do? How do we solve for a and a1 and a2 and b2? The exact same thing we did before. So either strategic substitution or equating both. Okay. questions on this and why we need that extra term? So let's look at a specific example. Let's find the partial fraction decomposition for 1 over 2x plus 3 times x squared plus 4. So first of all, is the degree of the numerator less than the degree of the denominator? That always has to be true to do this. Yes, the degree of the numerator is 0, right? The degree of constant is 0. Okay, so, and the degree of the denominator is 3, right? Does everyone see the degree of the denominator is 3 when you actually expand that out? If I were to actually multiply this out, I'm not going to, because the whole point is I want to keep it factored. But if I multiply that out, I would get 2x cubed, right? And so that's where that degree 3 is coming from. Okay, so we want to write this partial fraction decomposition down. Well, we know that our partial fraction decomposition, the part for 2x plus 3, that's just going to look like x over 2x plus 3. Sorry, a over 2x plus 3, my bad. Plus, and then for the quadratic factor, x squared plus 4, we have to have a partial fraction decomposition that looks like bx plus c over x squared plus 4. No way around it. We have to have it. But then from there, again, pretend that you don't know that this is where this came from. And I gave you this and I said simplify. What would you do next? Is a common denominator. And again, by design, the common denominator is 2x plus 3 times x squared plus 4. So the common denominator, I'll multiply top and bottom here by x squared plus 4 over x squared plus 4. Now get a times x squared plus 4 over 2x plus 3 times x squared plus 4. Plus bx plus c over x squared plus 4. Well, again, common denominator is 2x plus 3 times x squared plus 4. So I'll multiply top and bottom by 2x plus 3. And then I have a common denominator, so I can just write these over 1, right? So I have this fraction below here is supposed to be equal to this. If we pick A and B and C correctly, so the denominator is equal, that means their numerator has to be equal. So that means I get the equation. Well, the numerator of the thing on the left is 1. The numerator of the thing on the right is A times x squared plus 4 plus bx plus c times 2x plus 3. All right, and I'm going to solve this one by equating coefficients because I haven't done a full example like that yet. Also, when you have quadratic factors that you can't reduce anymore, all of a sudden from that factor, there's nothing I can plug in to make it 0, right? No real number. So let's look at with quadratic factors. A lot of the times, equating coefficients is going to be the easiest thing. So let's look at this. So I trusted myself. So the left-hand side is still 1. The right-hand side, let's expand everything. So the right-hand side, I'm going to get ax squared plus 4a. From the term. And then the second term, let's, you can FOIL it, call it whatever you want, distribute. I'm gonna get 2bx squared plus 3bx plus 2cx, and then plus 3. And now let's regroup everything in terms of the x's. So I still have 1 is equal to, well, my x squared, what's going to be in front of x squared? I'm going to have a plus a 2b. That's everything that's in front of an x squared. I factor those out. Or really, I factor x squared out. Plus, all right, what's in front of an x? Well, a 3b and a 2c, right? That's the only stuff that's in front of something that's x to the first. And then my constant term is plus 4a plus 3. Question? All right, so this tells me what? Well, the left-hand side is really 1 plus 0x squared plus 0x, right? So what does a plus 2b have to be equal to? A plus 2b is the coefficient on x squared on the right. So what's the coefficient of x squared on the left? 0. There's no x squared on the left, right? So a plus 2b has to be 0. What does 3b plus 2c have to be equal to?
0.
Perfect, 0 as well. And lastly, 4a plus 3c. 1, exactly right. So we get these 3 equations and 3 unknowns, right? So I'm going to do good old fashioned solve one equation, plug it into the next one, solve that, plug it into the last. Okay? So this one tells me that a is equal to minus 2b. This one tells me that let's solve this one for c in terms of b, and then the last equation will only have a b, right? So this one tells me 2c is equal to minus 3b, or in other words, c is equal to minus 3 over 2b. So I have a in terms of b, I have c in terms of b. I can plug those both into the last equation. So 4 times a, well, that's 4 times minus 2b, plus 3 times c, well, that's 3 times minus 3 times b. That's still equal to 1. So this tells me negative 8b minus 9 over 2 1. Negative 8 is negative 16 over 2, so negative 16b minus 9b 1. Just me simplifying this, right? So negative 25, I'll multiply both sides by 2, and I'll add the top up. So I get negative 25b is equal to 2. Or in other words, b is negative 2 over 25. And then I can solve for a. A is negative 2b. So a is negative 2 times negative 2 over 25. So a is positive 4 over 25. And c, Well, c is -3/2 times b, so that's going to be +3. Okay. So let me actually write down this partial fraction decomposition then. Okay. We have 1/2x+3 times x² + 4 equals a was 4/25. 8/2x+3, that's the same thing as 8 times 1/2x+3. Plus, we're going to write this out on the top. B was -2/25 x, and then plus c was 3/25. 4. And then to get rid of that 25, not over 25, you can multiply top and bottom of this. You can't really get rid of that, but multiply top and bottom by 25, right? And when you do that, you'll end up with 4/25 times 1/2x plus -2x + 3. I multiply the top by 25, I'll multiply the bottom by 25 as well. There we go. Okay, I can get 4/25, yeah. So it's the same idea. It is. It's a over that. So the exactly, yeah. Okay, so the second one is all of this. Dx plus c. Yeah. Yeah, it's really insane that this method works out. So, I mean, the numbers kind of suck. However, I would argue it's better to have crappy numbers than crappy integers. Because trying to integrate this without any knowledge of a nicer form of that sucks. But integrating this, as we'll see, sucks. All right, so let me copy this again. Copy. Did all that work. Why should I not copy it? Take still. We're about to do this integral. And we're going to see how partial fractions helps us in the case of quadratic fractions. Okay? So this integral, find this integral. Well, we just found that the thing on the inside was the same as this, right? So this is equal to, let's actually work this out together. 4/25 times the integral of 1/2x plus 3 dx. Plus, I'm going to pull out the 1/25 from this integral. So 1/25 times the integral of -2x plus 3 over x squared plus 4 dx. Okay. How would we handle this integral? Yeah, that's a u substitution. I'll actually write that one out. So u here is u equals 2x plus 3, which means du is 2 dx. Or in other words, 1/2 du is dx. So that first integral is going to end up being a natural log of 2x plus 3 times some constant. It's easy to see. This integral you need to look at a little more closely. So let's look at this the second. The integral of -2x plus 3 over x squared plus 4 dx. There's a constant down in front of it, but right now I just want to look at it. How would we handle this? And what we're about to do is going to be yeah, exactly right. So this plus 3 is screwing that up, right? But remember how we add fractions. I can break this up into minus 2x over x squared plus 4 dx plus the integral of 3 over x squared plus 4 dx. Jet was exactly right. A u substitution handled this part perfectly. Does anyone recognize? We've seen it before. I think it was on example. That integral. What if I divide top and bottom by 4? Then this is the integral of 3 over 4. Yeah. Times x squared over 4 plus 1. And what kind of integral? Arctan, exactly. And this is going to be true in general. Whenever we have a quadratic factor in partial fraction decomposition, you're going to get this part that you can handle with the u substitution. And then you're going to get this part that you're going to handle with, in general, a trig substitution. Here, the quadratic factor is nice, and we just know right away that that's the arctan of x over 2. So let's actually write this out to finish our class, and then tomorrow we're going to talk about, well, what about repeating quadratic? That's the last case I know. That's the last case we have to deal with, and then you know everything there is to know about partial fraction decomposition. So, actually writing this integral out, this one in particular. The other two you guys can handle, but as a reminder, how do you handle this one? Well, this is, I'm going to pull it 3 over 4 out from here. 3 over 4 times 1 over, I'm going to write this as x over 2 squared. 1 x, and then I let u be x over 2. du is 1/2 dx, in other words, 2 du is dx. So this integral becomes 3 over 4 times the integral of 2 du over 1 plus u squared. Well, this 2 and this 1/4 are going to cancel to just give me 3 over 2, right? And so this is going to become 3/2 times, from our memory, we know that that's the arctangent of u plus some constant, which is 3/2 times the arctangent of x over 2 plus. The 2, there was a 2 here, but there was also a 4 here. Yeah, exactly. So that's how that second integral is handled. If you want extra credit on the next exam, write out the full solution to this. Or in other words, actually do that integral, send me the solution, and I'll let you know if you're right. You get an extra credit point on the next exam. Okay, so finish integral for +1 extra credit on exam 2, which I am planning on holding before spring break. Questions? Quadratic factors, check. Tomorrow we learn about repeated quadratic factors, and then that's all there is for partial fractions. I'll explain why that's all there is tomorrow. Thank you all for being here. Have a great day. Let me know if you have questions. I'm here to help.
Thank you.